Okay. So, chemo brain is a brain injury. A brain injury changes the structure or function of the brain. Lots of things can do that. So let's take a look at a partial list. Next, please. Awesome. Okay. Did that advance everybody can see causes of brain injury? Okay, wonderful. So I won't drag you kicking and screaming through all of these, but suffice it to say, a lot of things can go amiss and change the way the brain works. Everything from an aneurysm, a bulging blood vessel in the brain, to anoxia, not enough oxygen in the brain. Let me just mention as we dive in here, let me invite this person to join us, that I am going to share this presentation with Monica to send to all of you if you would like it, and as well as some suggestions for further reading. So you'll have all these slides if they interest you. So we're talking about different causes of brain injury, medical causes. You can see that one of them is toxic exposure, including neurotoxins. Chemo brain is a neurotoxic brain injury. You notice here as well that a tumor can cause a brain injury. I heard one person share that that's been her experience. The brain is the consistency of jello. So you can think of a tumor like a golf ball suspended in jello. It is going to change the structure of the brain. And if it needs to be operated on, there's no way to slice through jello to get to the golf ball. You have to go through the healthy tissue to get to the tumor. And a golf ball is not a perfect analogy because a tumor has tentacles going into the healthy tissue. So a lot of times a person has to lose some healthy brain tissue when the tumor is excised. So those are some examples of things that can cause brain injury. The most common type of brain injury is a traumatic brain injury, which is caused by an external force to the brain. And here you see some examples like a concussion that you could get from a fall or in a sports setting. You could have a gunshot wound. You could be in a car accident. We have a lot of cases of children with abusive head trauma. So something where a force outside the brain damages it is a traumatic brain injury. The reason I wanted to start with this is because brain trauma is cumulative. So if you have prior brain injury, such as a traumatic brain injury, then chemo brain is going to affect you more because you're starting with a brain that is more vulnerable. How are we doing so far? Everybody hearing okay? Am I going at a good pace? Okay. I will just say, from my point of view, you can ask questions anytime, and I'm happy to answer. We can also have questions and discussion at the end. So whatever makes you happy. So with that, let's go forward, Monica. Okay, great. So just saying a word more here about traumatic brain injury. Again, that's if an external force damages the brain. It can be that the head hits an object or is hit, or that the skull is penetrated, or even if the head is never struck, but the body is violently shaken, causing the head to move forward and back. And you can see depicted there a common type of traumatic brain injury called a coup contre coup, meaning the brain strikes one side of the skull and then slams back and strikes the opposite side. I mentioned that the brain is the consistency of jello. It is floating inside the skull. If we go to the next slide, you can see that the interior of the skull has sharp, jagged ridges. Looking at this skull, the top is the front and the bottom is the back. This is why that's important. Do you see, oh, can we go back one slide? Do you mind? Thank you, Monica. I'm almost to the next one, but I just wanted to show briefly there. Do you see how the interior of the skull has sharp, jagged ridges? And most of them are in the front or sides of the skull. Mm-hmm. That is going to become important in just a moment. So I want you to remember that the inside of the skull has sharp, jagged ridges, and they're worst, they're most dangerous at the top or front and sides of the brain. Okay, thank you, Monica. So let's go forward here. And I want to do just a little bit of brain basics. I feel like if I dive right into chemo brain, we probably will just be wandering around aimlessly versus if we got a foundation, then when we add chemo brain, it'll make more sense. Is that okay if I do a little kind of brain 101, how the brain is put together, how it works? Okay, if at any point it's too much, tell me and I will jump ahead. But let's go forward a slide here, Monica, and have a look at the major parts of the brain. And again, I promise I'm not going to go too deep with this, but I think a basic understanding is very helpful. So for our purposes tonight, the brain has four major parts. On the top, there is a large wrinkled part. If you were to unfold it, it would be the size of a pillowcase, but it's all folded up and wrinkled and fits inside your head. That is the cerebral cortex. That is higher order thinking. It's reading, writing, speaking, your personality. In the center of the brain is the limbic system. The limbic system is your primitive brain. It is the center of fear and rage. If your head were a cantaloupe, the limbic system would be the pit of the cantaloupe. It's deep in the middle of the brain. Hitched to the back of the brain is the cerebellum that coordinates the body's movement. Last is the brainstem coming up out of the spinal cord, and the brainstem controls the basic functions of life. Next, please. I'm just going to kind of do a quick little tour here of the outside of the brain. And again, you'll get this slideshow if you'd like it, so you can have this. But let me just start in the bottom right here, talking about that brainstem. The brainstem keeps you alive. It's got your breathing, your heart rate, your blood pressure. It controls consciousness, being aware of yourself and your environment. It regulates your sleep-wake cycle and has very elemental forms of attention and concentration. Next, please. The cerebellum, I mentioned, hitched to the back of the brain, coordinates the body's balance and movement. Next, you see the first lobe or section of that wrinkled cerebral cortex at the top. There are four of them. At the back is the occipital lobe. This is your vision. You don't see with your eyes, you see with your brain. Your eyes bring the stimuli to your brain, but it's your brain that processes what you see. Next, at the top of the brain, we have the parietal lobe, which gives your sense of touch and taste, your ability to differentiate size, color, and shape, your depth perception. Next, you can see the frontal lobe. The frontal lobe is a third of your brain. It is the biggest part of your brain by far. And you can see what valuable functions are in this brain real estate. Your ability to solve problems, your ability to exercise self-control, your personality, your emotions, your ability to speak. And finally, if we give one more click, we'll get the temporal lobe, which is between your ears. It has your memory. It processes your hearing. It has your ability to produce and process language, your musical awareness, and your ability to organize things and put them in the right sequence. No matter what part of the head is struck, the part most often damaged is the frontal lobe. I'm going to say that again. No matter the part of the head struck, the one lobe most damaged is the frontal lobe. And that is because that is where those sharp, jagged ridges are. The second most damaged is the temporal lobe for that reason. Because again, the brain is bouncing around in the skull. So even if you fall and hit the back of your head, you'll probably have some trouble with your vision. Has anybody ever done that where you fall and hit the back of your head and you see stars? Has that ever happened to anybody? Sometimes that's happened to folks, and that's because you're touching that vision center of the brain. Any questions on what is where in our list of brain functions here?
I have a question. Can you repeat the second most damaged lobe with injury?
Yes, temporal. The temporal lobe between the ears is the second most damaged.
Okay, thank you.
You're welcome. Any other questions so far? Okay, so this is the outside of the brain. Now I'm going to show you the inside. So let's go forward. Thank you, Monica. Okay, first let's get our bearings, because part of this we already recognize, right? If we start at the top, we've got the frontal lobe, and then we've got the parietal lobe kind of on the top. We got the occipital lobe in the back with the vision, the cerebellum for movement, the brain stem. So some of this looks familiar, correct?
Mm-hmm.
Now, do you see the part labeled the corpus callosum? That is a band of fibers about the width of a pencil that connects the two hemispheres. Your brain has a left and a right hemisphere. So the left hemisphere controls the right side of the body, and the right hemisphere controls the left side of the body. Have you ever heard that somebody is left-brained or right-brained? Have you heard that term before? Yeah, that largely holds up. The left brain is more analytical. It's more focused on words and logic. And the right hemisphere is pictures, music, art, peace, joy, and love, that sort of thing. But the reason you experience the world as a seamlessly integrated place is because thousands of messages per second are transmitted across the corpus callosum. So in other words, I mentioned that the temporal lobe has your memory. Let me be just a little bit more specific. The left temporal lobe has your memory for words. The right temporal lobe has your memory for pictures. So when I see you, Amelia, what my brain is doing, I say, oh, hi, Amelia. What my brain is doing is this. It's getting your name from my left temporal lobe, and it's getting your face from my right temporal lobe. But again, we experience it seamlessly because the corpus callosum is putting those two pieces together thousands of times per second. Thousands of times per second. So far we've said we've got a left and a right hemisphere. We've got 4 major lobes in that big wrinkled cortex at the top. Is everybody with me so far? I'm going to do just a little bit more anatomy if you're okay with it. Is it okay if we talk about what's in the middle here? The colorful pieces? Okay. Remember how I said the pit of the cantaloupe is the limbic system, the primitive part of the brain? So what I want to explain to you is how your brain is working right now and every second of your life. Are you ready? Okay. So every second of your life, this is what's happening. You're experiencing the world. Things are coming in from your senses. The first place all of that information goes is right into the middle of the brain, the thalamus. That is the olive green lima bean shape that you see. So first, everything comes in through your senses and goes to the thalamus. So if it came from your eyes, it goes to the thalamus. And the thalamus says, oh, this came from the eyes. Let me send it back to the occipital lobe because that's where vision is processed. So the occipital lobe processes it and sends it. Oh, did I lose? Or did somebody have a question? I thought I heard a voice. Okay. So the occipital lobe processes it and sends it back to the thalamus. So the thalamus is the major relay station for all of the senses. Is it okay if we go back a couple? Oops, we almost had it. There we go. Perfect. Okay. So again, what we're covering right now is how the brain works every second of your life. The first thing that happens is that all of the senses first send their information to the thalamus, and then the thalamus sends it to the right lobe. Hi there, is that someone chiming in with a question or comment? No? Okay. Let me know if you need anything. Okay, so then let's say vision, for instance. Something comes from your eyes, it goes to the thalamus, goes back to the occipital lobe, back to the thalamus. Now, this is extremely important. Where it goes next is the amygdala, which is that tiny rust-colored pea-sized structure. The amygdala has your fight, flight, or freeze reflex. It stores your phobias and your traumatic memories. It is the center of fear and rage. So every moment of every day, the amygdala is always asking, is there something to be terrified of or something to be enraged about? And if the answer to either of those questions is yes, then whatever you're experiencing never even makes it up to the fancy frontal lobe where we have logic and reasoning and all that good stuff. You go to fight or flight as opposed to being able to act rationally.
Do you know anyone who?
No, I don't. I don't know.
Would you?
Girl Scouts. They were doing a stamp collecting merit badge.
Is there anything you would like me to do? I do hear some voices in the background, which is okay.
That is Ann's phone.
Oh,
I don't
hi,
know
Ann.
who it is. It says Ann's iPhone.
Yeah. Did you have a question or a comment, Anne?
No, it says my.
Oh, now you're muted.
Apparently, I'm
Okay.
not muted.
Now you're unmuted. If you want me to mute you, I can give it a try.
Please mute me because I don't seem to be able to mute myself. And then when sounds happen here, it's.
Okay. Well, it shows that I muted Anne's iPhone, so we'll give that a try. Okay, so again, what we're just covering is how the brain works every moment of your life. The sensory information comes to the thalamus, it gets processed in the right lobe, and then it goes to the amygdala, which is a gatekeeper for fear and rage. So if something triggers your fear or rage, you don't act logically or rationally the way you would if the frontal lobe is in charge. You go into fight or flight mode. Now, if what you're experiencing goes to your amygdala and the amygdala says, there's nothing to be terrified of, there's nothing to be enraged about, then the amygdala sends it next door to that circled lavender shape, the hippocampus. The hippocampus is where you learn new things. The hippocampus is also what stores that new information in your memory in the temporal lobe and gets it back out of the temporal lobe, what we would call remembering. Now I'm going to say just one more thing about this slide. It takes a minimum of 8 seconds of focused attention for the hippocampus to move new information into long-term memory in the temporal lobe. I'm going to say that again. It takes a minimum of 8 seconds of focused attention for the hippocampus to move new information into long-term memory in the temporal lobe. And it can take that long to get it back out as well. The reason I'm emphasizing that is this. I find sometimes people think they have a problem with their memory when really the problem they have is with attention, that they're not able to hold their attention on something long enough for the hippocampus to move it into memory in the temporal lobe. Any questions or comments?
Well, my question is, can the brain heal itself? Or if there's damage done in one area, say with a tumor or something, you just cope with it as best you can?
Great question. So the question is, can the brain heal itself? Or if there's damage in one area, such as from a tumor, do you just need to cope with it as best you can? Fabulous question. Let me give you a few layers to it. Number one, every brain is unique. That's what makes us all unique individuals. And so we can never predict ahead of time who can regenerate brain tissue and who can't. And we don't know how long they're going to regenerate that tissue. So yes, there is such a thing as neuroplasticity where the brain grows new connections, but we can't promise a person that because it doesn't always work out. The second thing to say about plasticity is that it can be adaptive or maladaptive. In other words, I feel like a lot of the splashy headlines about the brain rewiring itself make it sound like that's a uniformly positive thing. However, it is not. Sometimes when the brain grows new connections, they don't work properly. And so, yes, the person can start to do things, but not the way we might like. A classic example is after a stroke. To start with, a person may not be able to speak, and then as they regrow connections, they may only curse. Which, I mean, yes, that's speaking, but in a lot of social settings, that's really not what we ideally would want. And so it's one of those things where we hope we can regrow brain tissue. And where I'm going to end my talk tonight is on brain health, which will give you the greatest chance of having your brain grow new connections to take the place of ones that have been lost.
Are there areas that will heal or rewire better than others?
Oh, that's a great question. Some of this depends on your age. And I'm not trying to start a battle of the sexes here, but for the male brain, it finishes development between 29 and 30. The female brain finishes development between 21 and 22. So if a person is under the ages of those development deadlines, then they're going to have more growth because they're in that process anyway. The frontal lobe is the last lobe in both sexes to develop. And incidentally, it is the first one to deteriorate with age. On average, starting at age 40, we lose 1% of our brain tissue a year. That means that for a typical person, by age 70, we have lost an inch of brain tissue. But again, where I'm going to wrap up tonight is talking about taking care of your brain to hopefully combat that. So the only thing I can say to shed any light on that would be if the person has not had a fully developed brain, they would get more brain growth in those areas. But then once they're past that maturation, there is no set formula of which section of the brain will grow more quickly.
Okay,
Okay.
yeah.
Any other questions? Oh, or please go ahead.
No,
Go right ahead. Go right ahead.
Jump in. So, like, I have a problem in the cerebellum, so my balance is very
Yep.
bad, and I'm hoping that will get a little better, but maybe it won't, right? Maybe my
Well,
balance will always-
right, exactly. And one thing I will tell you is this, it takes a lot of repetition. There's a saying in neurology that neurons that fire together wire together. So in other words, you have to do the same thing over and over and over again to increase the chances that they'll grow connections between each other.
Interesting.
So a lot of times people kind of get bored and they don't want to stick with it. I mean, it can be 1,000 repetitions of the same thing to grow a connection. And people may think, well, I'll do 10 or 100, but I'm not going to do 1,000 of the same thing. So, you know, your best bet is definitely persistence and doing it the same way each time.
I have a question. Is that similar, Jessica, to like muscle memory? What, or is that completely different?
Oh, that's a great question. So muscle memory is a wonderful expression. We all know what we mean by it, right? But just to clarify, muscle memory is not in your muscles, it is in your brain. And yes, it is in the cerebellum. And the reason we call it muscle memory is because we are doing it without conscious effort. That's what we mean by muscle memory. We mean that the brain is doing this on autopilot. For instance, let's say you can walk. If you can walk, you probably walk across the room and you don't think, okay, now I'm going to lift my right heel 10 millimeters. And then I'm going to, you see what I mean? Like you're not thinking through all of that because it's not happening with conscious effort. But with brain injury, including chemo brain, a lot of what had been done without conscious effort now requires conscious effort, which is part of the reason a person is so fatigued, is because the brain has to spend all this energy consciously doing things that used to be done with no conscious effort. Yes, so Amelia, each one of these parts of the brain is working on a conscious and an unconscious level. An example would be the amygdala. A person may be aware of their trauma and they know what they're traumatized by, but someone who was traumatized as a very young baby, they're not going to have any memory of what they were traumatized by, but the amygdala will still be triggered by something, even though the person does not have a conscious awareness of why. So yes, every part of the brain is working on a conscious and an unconscious or subconscious level. Okay, so this middle part of the brain is the limbic system, and it stays the same from the day you're born all the way through your life. So if I didn't put you to sleep, Monica, if you can go forward a slide, I just have this picture that I love because I feel like it shows our inner child very well. Oh, are you with me, Monica? Did I put the system to sleep with my long answer?
Oh, the computer is doing some weird stuff and
Oh,
it's,
no, I'm sorry about that. I wonder if I made it,
no, it's not you. So
okay.
give me, I will keep talking and I will try to figure this out.
She's gonna
Okay.
exercise persistence.
There you go. I do have the little forward button here, but I don't think if I touch it, it'll do anything. I'm just gonna try and see if it's a touch
Try it.
screen. It was worth a shot. But
Yeah. I am having issues. So
okay. Well, do you want to try, this is just an experiment, but do you want to try stopping it and like starting, you know what I mean? I don't mean stopping the whole Zoom, but just like stopping it and then letting us go. Oh, I think I went forward on my screen. Did it go forward for everyone?
Yes.
Are we all on the
I'm
same?
doing a happy dance over here, guys.
Oh, that's hysterical. That's so
Do you see why I love this
cute.
picture? So what
Aw.
this is showing is no matter how grown up we are on the outside, our limbic system is our inner child. It does not mature. And we said that the amygdala is your center of fear and rage. The hippocampus is where we learn and remember things. And this is extremely important. The frontal lobes, where we have self-control, are less active when we're sleep deprived or stressed. The brain runs on electricity, and they hook electrodes up to people's heads. And when they are very sleep deprived or very stressed, the frontal lobe, where we act like grown-ups, is dark. And the limbic system, the pit of the cantaloupe, our inner child, is lit up like a holiday display. What I am telling you is, think of the most together person you know. This person could be a Zen master, but I am telling you this, if you get that person tired enough or stressed enough, you will bring out their inner toddler, because we never lose this person. It's just that our frontal lobe is controlling our limbic system. But when we're too tired and too stressed, the frontal lobe says, I don't have enough energy to keep this system going. I'm going to stick with what's keeping you alive, the limbic system and the brainstem. You know how, like, when you go outside in the winter, if you don't have all your gear on, right, what gets cold first? Your fingers, your toes, right? Because your body's like, let's put the blood in the core where the organs are. That's how the brain is. If you don't have enough energy to run the whole operation, it says, oh, we can skip fancy things like logic and self-control. We're going to put our limited energy into fight, flight, right? Fear, rage, survival mode. And so, again, no matter how much we may wish to be different, we all have this inner child because that limbic system does not mature. Okay, so just if it is possible to go forward, perfect. And you could go ahead and hit it one or two more times there, Monica. I just want to briefly show, again, if you've had a TBI, you could have that the brain has scraped against the front or sides of the brain. You could have a situation where the skull has fractured and there's just damage in one spot. And then one more click from you, Monica, if you don't mind. You could also have a diffuse axonal injury. And I just want to give you encouragement. We're only 2 slides away from where I show you what chemo is doing in the brain. So we're almost there. But a diffuse axonal injury would be something like a concussion, where the brain is shaken up. It's diffuse because it's the whole brain. And it's damage to the axons, the long connecting fibers between brain cells. Okay, so I showed you the outside of the brain, the inside of the brain. Now I'm going to start to show you the brain at a cellular level, like individual brain cells, which will lead us to what chemo is doing to those cells. Everybody good? Okay, so a diffuse axonal injury, such as a concussion, first, down the left side, let's look at what a normal neuron looks like. Neurons send signals. I'm going to say that again. Neurons send signals. That's what neurons do. I said the brain runs on electricity, so let me be more specific. Neurons send electrical signals to each other. So a neuron sends a signal down that long axon to its neighbor. In the upper right, you can kind of see zoomed in what it looks like when two neurons interact. You get the end of the axon of one cell, and then the synapse is the juncture or junction of two neurons. Dendrites are what the axons sprout for additional connections. Here's what I want you to know. The more connections you have between two cells, the better you are at what those cells do. The more connections you have between neurons, the better you are at what those neurons are in charge of. So when I was talking earlier about you need a lot of persistence and repetition to grow new connections, this is what I'm talking about. Growing new axons and sprouting new dendrites off of them. The way I think of it is this. Let's say I'm a neuron and you're a neuron, okay? Your cell body is your body. You can think of your arm as an axon, and you can think of your fingers as dendrites. That's about the right scale. Cell body, axon, dendrites. Now, in the bottom right, we see what happens in the brain in a diffuse axonal injury, such as a concussion. You can see that in illustration A, when you've got that force applied to the brain, the axon can twist so that it pulls away from its neighboring synapse. Do you see how there aren't as many dendrites touching? Do you see that? How you still have dendrites, but they're not all touching like they were before? Can everybody see that in the A illustration, the twisted axon, that the axon looks okay, but it has twisted so that those little yellow dendrites at the bottom, there's only one touching instead of all of them touching? That means that the two cells can still talk to each other, but it will be slow because there's not as many connections. The more connections you have, the faster and better it is. I'll give the example of speech. If you twisted an axon in the part of the brain that controls speech, you could still speak, but you would speak slower. The next illustration shows a torn axon, and you can see the dendrites touch, but the protective coating on the axon has torn. That means that the signals will still arrive, but not in a pristine condition. So the person would still speak, but their speech would be slurred. And then in the last one, where the axon is broken entirely, the person couldn't speak at all. So again, up until this point, what we've talked about is the brain in general and how it can be injured in something like a concussion or a traumatic brain injury. Where I'm going to head next is chemo brain and what's happening in the brain. Do I have any questions on this part before we dive into that? Anything we've covered so far?
So if you had something like a broken axon, is there a lot of those or just a few? Like if you have a brain injury, how many axons are getting harmed?
Oh, that's a great question. So you have 100 billion neurons, and each of those neurons can have an axon to a neighbor, and they can often have as many as 10,000 connections with another neuron. If it's something you're really good at, you've got a lot of connections. So you can afford to break a lot of axons and still have the brain work pretty well for a time. Here's the problem. Unlike a broken leg, a broken axon does not knit back together. Instead, it withers and drops into the cerebral spinal fluid that circulates in the brain. Axons are hollow, which means that the broken axons are now floating in the fluid that floats down the existing axons. Do you see how that would clog up the existing axons? The end result, when you get enough broken and clogged axons, you have dementia. That is why people with a history of traumatic brain injury have an increased risk of early onset dementia. So yes, you can afford to break a lot of axons, but there is a tipping point where you've broken too many and clogged too many of what's left. And to give you a sense of scale, an axon, think of a single human hair. An axon is 100 times thinner than a single human hair. That is how fragile the connections in the brain are. So you could see how something like a concussion, which is seen as mild, if you're shaking up your whole brain, it wouldn't take a lot of force to twist, tear, or break a lot of axons at once. Any other questions? Well, you've been a very good group. You've been good sports while I dragged you through all that. And now to the headline, chemo brain. Okay, now we are going to camp out on this slide because there's a lot going on. But this is what we're here to talk about. So first of all, let's start with what we recognize. Those mustard colored shapes, the neurons. Everybody with me? We can see two neurons, okay? And I just want to remind us that neurons send signals. We've got 100 billion neurons. They send signals to each other. Neurons get all the press, but there are 10 times as many glial cells as there are neurons. Glial cells support neurons. Sometimes glial cells are called helper cells because they help or support the neurons. The headline is chemotherapy in many of its forms greatly impairs and sometimes even kills the glial cells. So not the neurons, but the helper cells that enable the neurons to function. So this slide shows 3 glial or helper cells: microglia, oligodendrocytes, and astrocytes. I'm going to start in the top right with oligodendrocytes. I'm starting there because there's part of this we already recognize. Do you remember the prior slide? We said there was a protective coating on the axon that got torn potentially. That protective coating is the myelin sheath. That works like an insulating layer. You know what? It's almost like, I'm not mechanically inclined, but I believe that like a copper wire can have some kind of, rubber coating or insulation over it. It's that principle. So oligodendrocytes produce the myelin that coat the axons. What that does is enable those electrical signals to go from one neuron to the other quickly, correctly, working great. Well, some forms of chemotherapy kill oligodendrocytes. Sometimes they kill them temporarily, just while chemotherapy is happening, and sometimes they kill them permanently. Well, they say permanently, they just mean in the space of the study. When they went back years later, the person still didn't have oligodendrocytes. So when I say permanent, I mean, I guess, they never followed somebody for 80 years, but, over many years, still no oligodendrocytes. So you still have your axon, you still have your neurons, but you don't have that protective coating. Myelin needs to be continuously replenished. So when you lose your oligodendrocytes, you eventually lose your myelin sheath, you lose that protective coating on the axon that conducts the signals between neurons.
Excuse me. I'm wondering if
Kimberly.
I'm wondering if you can tell, you've mentioned a couple of times certain types of chemotherapy. Can you be specific about which types of chemotherapy would actually be damaging this area?
That's a great question. What is studied the most is I'm going to stumble over it. Methotrexate. That's what I'm trying to say. Methotrexate. That's in a lot of forms of chemotherapy, and that methotrexate is always one of the culprits for what we're talking about right now. And when I send Monica the email with this presentation and the links for further reading, I'm going to include studies and and they're very detailed as far as what kind of chemotherapeutic agents were studied. I freely admit I'm not an expert on chemotherapy, so I want to be a little careful not to be like, well, this one does this and this one does that. But I will say this is a common situation. However, you're pointing out something very important, Kimberly, which is sometimes you don't really have a lot of options with chemotherapy. They just say this is the drug that you need for your kind of cancer. But if you ever do have a choice, in my opinion, this topic is a valuable one to discuss with your treatment team. In other words, if you have a choice between two regimens, you could say, what is the difference between these two and what they do in the brain? Because if there's one that either doesn't hurt the oligodendrocytes or it's only temporary, maybe that would be part of your decision. Yes, Patricia.
Is there pain involved with the deterioration of the glial cells or the myelin sheath?
Oh, great question. What a good question. You guys are so much fun. Monica, tell me if I'm like way over my time because we'll be here till midnight. Okay, so 30 minutes, you said? Yes. Okay, so the brain cannot feel pain. In fact, they're doing brain surgery more often with people awake. They can slice into your brain and you won't feel a thing. So the brain does not feel pain. However, myelin is throughout the body, not just in the brain. So you won't feel pain from this process of losing myelin in the brain. However, with something like MS, where you lose the myelin in nerves throughout the body, that's a different thing because the brain and the spinal cord are the central nervous system. Oligodendrocytes produce myelin in the central nervous system. Schwann cells, SCHWAN cells, produce myelin in the peripheral nervous system, the rest of the body that is not the brain or spinal cord. Here's the big difference. Do you see how this oligodendrocyte is touching two axons? Do you see that? This blue guy is touching two of the axons? Well, oligodendrocytes can wrap up to 30 myelin sheaths around multiple axons. Schwann cells in the rest of the body, they only can wrap one myelin sheath around one axon. So if you get what I'm trying to get at is nerve pain in the rest of the body is going to be from losing myelin is going to be a lot worse because you only had one layer of myelin. That cell only wrapped one axon versus oligodendrocytes, they are producing a lot of protection for a lot of axons. But because the brain doesn't feel pain, when you lose it, you're not going to feel pain from it. And before anyone asks what a headache is pain receptors in the membranes that cover the brain. So the membranes that cover the brain have pain receptors, and that's what a headache is. But the brain itself, where these cells are, does not feel pain. So no, you should not feel pain from losing the myelination of axons in the brain.
I know we're talking brain, but I'm wondering about neuropathy. I don't know why. Is that related to the myelin sheath on the nervous system in the body, like RMS and things like that?
Yes, very much so, very much so. And I would love to go down that topic, but
Another
I want to
time.
be careful. No, you didn't do anything wrong, but
I can
just
look it
wanna
up.
be careful. Because I will definitely be tempted to go into other topics. Okay, so that's oligodendrocytes. Now, the other thing that something like methotrexate does is affect the microglia. The microglia, that's that little brown fuzzy guy, kind of to the center left of the screen. Microglia are the brain's immune cells. Microglia are the brain's immune cells. And what many chemotherapeutic agents do is produce long-term activation of the microglia. In other words, they start them up and they stay going, which is not what's supposed to happen. The microglia are just supposed to remove damaged neurons and fight infection. That's what they're supposed to do. Remove damaged neurons and fight infection. But with chemotherapy, those microglia get turned on and they stay activated again, sometimes for years, which then impairs the functioning of the last type of glial cell, the astrocytes. And astrocytes are what provide food or fuel to the neurons. Now, I want to say one more thing on this slide. In the bottom right, you see synapse. We said that's the junction between neurons. Well, one of the links I'm going to give you to talks about methotrexate and other agents that they, get this, they damage the synapses in the hippocampus. Remember, the hippocampus was learning and memory, right? So that brain fog, I can't remember things, I'm struggling to learn new things, that in part is explained by damage to the synapses in the hippocampus. And again, I'm going to send you links where you can, read as much as you want about this. And again, you've got my email, so you can send me any questions that you want. Do you have any questions about this slide at this time?
The brain fog learning hippocampus.
Yes.
Hippocampus. Can that be maintained or managed by learning activities, like learning something new? Or,
Yes, and that's where I'm headed. Yes, that's right where I'm headed. So that's a perfect segue. I'm gonna take you up on it, Patricia. Yes, so let's go to that next. So sure, Monica, can we go forward a slide? Oh, I may have lost mine. Do I have Monica? I think I
I'm
have
still
it.
here. I'm just trying to get it to go
Oh.
forward.
Are we ready is that okay if we go forward?
I don't think it's your hippocampus, Monica.
I don't know.
So if we go,
There we go.
Okay.
There you go.
Once again, I'm just going to make a brief comment, then I'm right to brain health, which is what your question was about, Patricia. So if we go one more slide, Monica, this is a brief but powerful list of strategies for managing chemo brain. They look simple, but they're deceptively powerful. The first one is to accept it. And by accept it, I don't mean you're okay with it. I mean, my definition of accept is that I do not waste energy resisting reality. So the reason that is so important that you not waste energy resisting the reality is because you need to manage your energy. You are not losing intelligence from chemotherapy. You're not losing intelligence, but you are losing mental stamina, cognitive energy. So you have to adjust your activities to protect yourself from emotional or cognitive overload. You probably cannot be as spontaneous. You need to have a plan of how you're going to manage your energy. And I'm a fan of telling people, it's not a shameful secret, and just being straightforward about it so they can manage their expectations accordingly, and being open to finding new and different things that bring you happiness. I mean, if you were a physics professor writing textbooks for fun, and now you don't have any oligodendrocytes to make myelin sheath on your brain axons, you may not be able to pull that off anymore, but that doesn't mean there aren't lots of other fun things to do. So basically, my message is live your life based on the brain you have today, not the brain you used to have or the brain you wish you had. With that said, we do want to make the most of the brain we have. So the last portion of my talk is how to maintain your brain health. And that includes things that would, grow the connections in the hippocampus. So on we go. And so this last part is about brain health. And just let me give a disclaimer here that before you change your lifestyle, I do want you to talk to your doctor. I'm not sharing anything controversial. These are all things that research has shown are good to take care of your brain. But I still want you to, get medical clearance just to make sure it all works well with you and your situation. So there are 6 tips. So as we go forward here, you can see first up is nutrition. The walls of your neurons are made of omega-3 fatty acids. I'm going to say that again. The walls of your neurons, like the cell walls of your neurons, are made of omega-3 fatty acids. So it's very good to eat omega-3s because they are like putting bricks in the wall. They're repairing any damage to the neuron's structure. So if we go forward, I've got some pictures here. So we'll do a few quick clicks here, Monica. So some examples would be things like fatty fish, like salmon or tuna. And going forward, we can see something like walnuts. Walnuts have the most omega-3s of any nut. And I remember they're good for the brain because to me, they look like little brains. You know, they've got their little hemispheres and stuff. So walnuts would be good. Going forward, I do want to talk you into some fruits and vegetables. Broccoli, and one more click, blueberries are particularly good for the brain because they fight inflammation. And so we really need that to have the brain work well. And if you didn't like any of those, if we go forward, really good for the brain is red and black beans. And finally, mushrooms. So those are some ideas of things that are data-driven to work well in maintaining the structure of your brain cells as well as their connectivity, how those synapses fire. Next, we can see drinking enough water. One more click there, Monica, just so we got the visual of the drinking water. I find that people, like, we drink everything, but we never get around to drinking water. The brain, you know how the lungs are 90% water? Well, the brain is 75% water. It's mostly water. And then of the part that's solid, the 25%, 60% of that is fat. So the brain is water and fat. So you need those things in order to take care of the brain. You remember how I talked about those hollow axons and that fluid that is flowing through them? Well, drinking water is what gives you enough cerebral spinal fluid to rinse out those axons and keep the connections working well. Next, please. Exercise. And we can do another click here just to show some movement. And again, this is like all the others, something I would want you to talk to your doctor about. We're not talking about anything wild, but just, 30 minutes, 5 times a week is the standard, but certainly that could differ for your situation. But here's the bottom line. What's good for the heart is good for the brain. So aerobic exercise that's good for the heart is also good for the brain. Bonus points if you can get your exercise in nature, which, no, that's good. That's perfect. Well, cognitive rest is my next tip. I don't see this covered a lot. This is good. This is good. Maybe back just a couple, but just to maybe the woods one. But yes, cognitive rest. You may say, isn't that sleep? Well, yes, sleep is extremely important. But if the only time you're resting your brain is when you're physically asleep, your brain is not getting enough rest. It is when you rest your brain that the brain organizes your memories, it takes out the trash, it boosts your creativity. So I'm giving you permission to daydream and stare off into space. That's not being lazy. That's maintaining your brain. You're supposed to let your brain just do nothing. And you don't have to be physically at rest. You could be physically active. You could be going for a walk, but you're just kind of zoned out and you're not solving any problems. You're just soaking up the atmosphere. Cognitive rest is very important for brain health. Okay. Next slide, please, Monica. Okay, now this is the flip side of that coin. I just told you to put your feet up and let your brain rest. Now I'm telling you the opposite. You have to make your brain work. No, not, when you're having a horrible day. I'm not talking about that. I'm saying when you're in a position where you can. It is very important to make your brain work. Remember how we said, starting at age 40, on average, we're losing 1% of our brain tissue a year. And that is not just natural aging. That's because for most of us, we get into kind of a rut. We get into a routine, we go the same places, we see the same people, and our brain doesn't have to work very hard. So if you want to fight that brain deterioration, you have to make your brain work. So on our next slide, you will see what I mean by challenging your brain. Number one is pay attention. You cannot form a memory if you did not hold your attention on something in the first place. Remember, we said earlier that you need at least 8 seconds of focused attention in order for the hippocampus to put something in long-term memory in the temporal lobe. So it's very important to pay attention, hold your attention on things. Use all 5 senses at once. That is a terrific brain exercise. A classic example would be something like cooking. You know, when you're cooking, you smell it, you hear it sizzling on the grill, you're tasting it, you're touching it. So all 5 senses at once is very good brain exercise. I get a lot of questions from people about, how do I improve my memory? We were talking before about, how can I get my hippocampus to work better? The bad news is the memory boosting apps, that's all nonsense. None of them work the way they claim. The most that doing a memory boosting app is going to do is make you better at that app, but it's not going to translate into having your memory work better in real life. To do that, you have to actually use your memory in real life. So I'm giving you some good examples here. One of them would be, and some of these may have to wait till after the pandemic, but if you go to a new place, when you get home, draw a map of how you got there and include as much detail as you can of what you saw. Another idea, if you meet a new person in the morning, notice 4 things about that person. And then later that afternoon, try to write down those 4 things that you noticed. Another example would be take out a piece of paper and pick a letter, maybe the letter G, and just try to write as many words as you can that start with that letter. Now, do you notice what all 3 of those approaches have in common? Did anything jump out at you?
Memory.
Memory, and specifically, how are we putting things in or out of memory? Through what
Writing them
mechanism?
down.
Writing. Mhm.
Writing.
Perfect. Writing. Do you see how every single one of them has physical writing, drawing a map, writing words, right? Research has shown that physically writing, piece of paper, pen, pencil, encodes things in memory much better than typing or hearing or thinking about them. So, actually physically writing things is very good for your memory. Reading, we all know that reading is great, right? Reading uses every part of your brain. And again, we may have to hold off on a little bit of this for the pandemic, but it is fabulous brain exercise to have in-person conversations. There are entire networks of your brain that are only used when you interact with a person in person. And so you want to use those networks to keep them from atrophying. So if you put the last 2 ideas together, a book club would be a fabulous thing to do, because you could read a book and then get together with other people and have conversations about it. Okay, Monica, we're almost done. Last one, connection. You can do all 5 of the other things and your brain will still atrophy if you don't have emotional connections with other people. I'm probably too late on time to give you any detailed examples from studies, but really and truly, it's just been shown over and over, all over the world, that people who have emotional connections maintain their brain health. Our brains interact with other brains. You can't keep your brain healthy, just your brain by yourself. It has to interact with other brains. And my last slide was, just in case you're wondering what 32 was, I just like this because it was connection in the shape of a brain. But you could go back a slide, Monica. I just didn't want anyone to be in suspense of what the last slide was. But where are we on time, Monica? 15 minutes. Did you say we have 15 minutes? Yeah. All right. Okay, wonderful. Well, I know I threw a lot at you. I'm very happy to take questions. If you want, do you guys like to be as a group? Like we can stop the slideshow so you can see all of each other together. Is that better?
Yeah.
Okay. Oh, good. I wasn't
Great.
sure. Hey, maybe they all left, but no, you were chiming in. And I got my little cheat sheet because I could see 13 people. So thank you for listening. Like I said, I really put you through your paces there and you were good sports about it. So questions, comments, Amelia?
So you talked about having in-person conversations, and with COVID and everything, have they done any studies to see if perhaps Zoom is better than nothing? I mean, you know what I mean? Like
Yes,
if
that's a
we're
good
not
question.
able to be with people, it's like the next best thing. And
Yes.
it's still a connection.
Yes, I agree with that. They're still working on the studies, but I will say that you've got exactly the right principle, which is some is better than none. So you don't want to just have it be like, well, if we can't be in person and we don't try anything, because first of all, it's still an emotional connection. However, when it's safe, because every once in a while I meet people who are like, this is wonderful. I never need to be around another human being for the rest of my life. I'm like, no, because for instance, when we're together in person, we smell each other. Not literally go up and sniff, but your brain can smell, I'm not kidding you, 1 trillion smells. That is how amazing the sense of smell is. So when you're around another person, it's your brain's chance to be like, ooh, let me work with the smell circuitry. So I know it's so corny, but it's so true. It is use it or lose it. If you don't use a part of your brain for long enough, your brain, hear me on this, stops sending blood to that region, which means that brain tissue dies. Now, if you take one day and put your feet up and read a trashy novel, your brain is not going to atrophy. But if you put your feet up for 5 years reading trashy novels, and then you try to do some analytical chemistry, you're going to struggle because your brain's going to be like, oh, I thought we weren't going to do any analytical thinking anymore. The brain wants to be efficient. So if you use it, it will maintain it. But if you're not using the brain, it's saying, I'm not wasting energy maintaining this thing you're not doing. So there's no getting around it. If you want to be able to do something, you have to do it. And an example I give, because we don't always think of it as a cognitive function, is making a new friend. Making a friend is a brain function. And there's some people, they haven't made a new friend since kindergarten. But if you ever want a new friend again, you have to actually make a friend. Your brain has to use that part of itself, or you will find, oh my goodness, I can't make a new friend. So anything you want to be able to do, you have to do. There's no substitute for it. Again, you can have days that you don't feel well and you give your brain a break. But I'm saying the general principle that if you want something to work, you have to actually make your brain do it, because otherwise your brain is going to say, why am I maintaining this? There's no point. Did I see a hand? Was that you, Sue B. in Pittsburgh? I thought I saw your hand. Don't let me put you on the spot, but did you have a question?
Yeah, I find that I have to make lists. And
Yes.
if I'm even going from point A to point B in the apartment, I'll get there. And if I don't have my little list, I will forget why I went there. And that's upsetting to me. But
Yeah.
I'm finding little ways to compensate. And I joke that I can't walk and chew gum. I used to multitask and it's like, no, I can't do that, because if I do, I'll fall.
Yep.
I have to focus.
Yep.
And my daughter has said to me, well, you're slow. Yes, I am slow, but I haven't fallen. And
Yeah.
I'm still here. But
Yes.
I don't function the way that I did.
Very true. Very true. And that is inescapable. You know, really, our behavior is brain plus environment. That's my equation. Brain plus environment equals behavior. So you have the brain you have, and then you're in the setting you're in, and you put those two things together and you get how you behave. So for instance, you're walking at the pace you can walk that you can safely walk. You know, if you were in another setting, you might need to walk either faster or slower to adjust to it. So it's brain plus environment equals behavior. You're absolutely right. And just, it says, we probably have heard this before, but multitasking is a myth. I mean, technically, it's just very rapid task switching. And not for nothing, it's extremely draining to the brain. Extremely draining to the brain to switch back and forth, back and forth, back and forth, back and forth. So all of us would do well to just give up on this multitasking nonsense and just do one thing at a time. Why? Because that is how we conserve brain energy. Think of it this way. Think of your mental energy like a battery. You know, you wake up in the morning and let's hope for the sake of this, you got a good night's rest, your battery's charged. Well, if you are bouncing back and forth like a ping pong ball, in the first hour of the day, you've drained 60% of your battery. Life with Chemo Brain is all about managing energy, plugging those energy leaks. Multitasking is wasting energy. Putting up with toxic people is wasting energy. Like, you just don't have the luxury of having things that are draining your mental energy because you need them for the things that matter most. Mm-hmm.
I think that's very important, is if I have limited energy right now, how am I going to spend that energy in the way that benefits me the most? And, you know, a couple of thoughts that came up is I try to focus on what I'm doing. Sometimes I say to myself, Stephanie, get back in the car you're driving.
Yeah.
Because my mind goes a million different places.
That is so valuable. Can I just tell you, even without Chemo Brain, and then I'll be to you, Amelia, even without Chemo Brain, the default state of the brain is inattentive. I think we have this myth of ourselves that we're these paragons of attention. That is not true. If you plop a person in a chair next to a window, they will look outside the window for a moment, and it won't take this long before their mind is going to be wandering. Right? It's just, we are not people that sit around and pay attention. You have to tell your brain to pay attention. And when, I'm not kidding, I mean, you saying it out loud is perfect, because research has shown that our brains believe what they hear our own voices say more than any other voice. So I do this, I don't mind looking silly in public, and I say to myself out loud, whether I'm in public or not, pay attention. Sometimes I'll snap my fingers or clap my hands like, woohoo, pay attention, because otherwise my mind will wander and I won't stay in the moment. So you absolutely need to tell your brain to pay attention. It's not what it does naturally. And Amelia, oh, I'm sorry, did you have a second thought? And then to Amelia, I wasn't sure if you had said.
Oh, the other thing that came up for me when we were talking about Zoom and then versus getting together with people in real life. And because I just had the opportunity to get together with some people in real life, I could not believe how much more information is coming in.
Yes.
It's bizarre, things I'd never noticed before.
Yes.
It's picking up a lot, and I can't even explain all of it, but there's emotional and
Yep.
Yeah.
And even with Zoom, we can, if we need to like run out the door or something, we can like turn off our video or we can mute the sound. When you're sitting across from a person, Like, you have to react in the moment. And if they say something shocking, you have to fix your face and not look shocked. It's like a lot of work, which is part of why we avoid it. It's like we'd rather text because then we don't need to see the person and it can be asynchronous or we can answer when we're ready. In person doesn't let you do any of that. You've got to react in the moment. You've got to do all the nonverbal communication. Like you said, it's a lot to process in the moment, but that's why it's a good brain workout. Yes. I'll be right to you, Dottie, but I had promised Amelia.
Oh, sorry, Amelia.
Well,
No, you're okay. I just had seen her hand.
yeah, my question is, you mentioned that there's really no official multitasking, that our brain is thinking and then it does the next thing, but how does that compare to like executive functioning, like where you might have to be thinking of a couple things at the same time? Like, for example, when you're driving, you don't just, you have to be taking in a lot of information and doing that. And obviously that takes a lot of cognitive energy. But I was just wondering how that compares and if that is helpful to like practice those things that are more executive functioning.
Good question. First of all, there is no contest. Driving is far and away the most cognitively demanding task that most of us do on a daily basis. There's nothing that compares to it. You've got to be paying attention to what's going on 360 degrees around you. You have to be reacting very quickly. You need to use all your senses. It's extremely demanding, and it upsets me greatly when people are like, on their phone or watching a movie or something, or having a call with the office. It's like just driving is more than enough for any one person to be doing at any one time. So yes, driving is a very good example of a very demanding cognitive task. Yes, it does use executive function, but even executive function, which means to make a plan, initiate it, carry it out, deal with distractions, and get to your end destination. So it could be driving somewhere, it could be filling out a form you've got to turn in, anything where it's like, I got to get from this point to this point. Even that though, it's still not happening, even though it looks like it's happening simultaneously, in the brain, it's one after the other. A tiny example I can give you of this, I think most of us feel like if we touch a hot stove, like we feel the heat and we move our hand, but again, that's two different things. We may feel like, well, I felt the heat and I instantly, no, that was two different brain things. One part of the brain, there was a stream that felt the heat. There was another part that moved your hand. So even when things happen very fast, there are always separate moments and tracks in the brain. So technically it's all task switching, not multitasking. I mean, I don't mind if you call it multitasking. I'm just saying in the brain, technically there's no such thing. It's task switching rapidly. And I think I saw Dottie.
Yes. Before we run out of time, this is to Jessica and Monica. I think this has been fantastic, and you've opened up incredible amounts of ideas. What are the chances of doing this at least one more time, maybe on a regular basis? Because I know I'm going to go away from this with 1,000 questions.
Yeah, well, I would love to come back, not to invite myself.
Yeah, her and I will talk about this afterwards, because I think she's got a lot of really valuable information about so many things.
The brain is such a vast topic, that there's really a lot to learn and talk about. I agree with that. Yes. Yeah. Well, thank you. Yes, Kimberly.
I was going to say that one of the things that I think would be really helpful is I'm sitting here and saying, I wish I had heard this information maybe 6 months ago, not as I'm finishing chemotherapy, because while I could say, oh, I did that, oh, yay for me, there's another gold star. There are things that if I had known them, I could have worked that consciously into just my plan to get through chemotherapy. So, I mean, if there's any way to, Monica, share this with people that are just starting chemotherapy, I think it would just be so valuable if they are really worried, as I was, about, because everybody talks about chemo brain. Am I going to get
Yes.
chemo brain? And,
Yep.
if I knew at the start, do these things, I would have been doing more of them. I'm sure, because I am afraid of losing
Mhm.
Function.
the connections that I've been able to make in the past that are now, they're not very strong right now in many
Yeah.
cases. So
Yeah. Thank you for that. It's a good suggestion.
It is a great suggestion. Yes, Amelia.
I also want to say, I listen to a lot of speakers, and I can tell you that the way you pause and the way you repeat things so that we can process the information is really helpful. So thank you very much as
Oh, well,
a
that's so
really
kind.
excellent presenter.
Oh, well, that means a
Mhm.
lot to me because I put thought and effort into that. So you know what I mean? Like I slow myself down and things like that. So it's gratifying to know that that is helpful to you. Because I find the brain very exciting. So I'm very tempted to just go 100 miles an hour. So it is very kind of you to share that, because that shows me that it's worth it to me to restrain myself and go at a reasonable pace, because I really don't want to overwhelm. I feel like this is all very understandable, I feel like we can all understand it, but you're right. If it comes in at 100 miles an hour, we're not going to get it. So thank you for that. And that's why I did ask a couple of times, is this a good pace? Because that was what I was driving at. Like, I don't want to be going too fast or too slow, so it's good to know that I hit right about right. Thank you for that.
Great job.
Yeah.
Really, it was fantastic.
Well, that means the world to me, because my mission in life is to just tell everybody. I cover 12 counties, and to just tell everybody who will listen about the brain. So this was about chemo brain, but I mean, if you've got a group you want me to come speak for, I want everybody to understand what is happening in the brain. And I do tailor my talk to every group. So this was chemo brain, so I went into that. If you wanted me to talk to someone else, then I would talk about what was relevant to their group. But I just really feel like, it sounds so corny, but knowledge is power. Kind of like what you were saying, Kimberly. It's like the more I can demystify it to say it's not your imagination, that you might be struggling with some things with chemo brain, but you're not entirely powerless, and here's some things to try. And I just think that's an empowering message. And you were very good sports about me using the technical terms, but I believe so strongly in that, because when you go to Google it, they're not going to call it a thingamajig. They're going to call it an oligodendrocyte, so I'm not doing you any favors if I let you off the hook. But at the same time, I don't want you to like fall asleep because it's this dry, brain terminology. So I try to make it technically correct, but still accessible. So, yeah.
You made it fascinating. I mean,
Oh,
curiosity to how the
well,
brain.
I really do feel like it's just extraordinary what the brain does. And, and you're going to laugh at this, but they have done a lot of studies that show that if you're nice to your brain, it performs better. So even silly things, if you say something funny, that was your brain doing that. So if you just quietly to yourself say, thank you, brain, that you came up with that little joke. They don't know the mechanism by which it works, just like they don't know why we respond to our own voice more than another one, but it's been shown. And that's why, self-talk is always so important, because what your brain hears you say, it believes. Well, my favorite study on this was with people quitting smoking. They didn't do Chantix, they didn't do hypnosis, they didn't chew gum. What they had folks do was, while they were smoking, they would say, I no longer smoke. I used to smoke, but I don't smoke anymore. The whole time they're smoking. And after 3 months of this, a surprising number of people quit smoking because the brain's like, oh, I guess we don't smoke anymore. I mean, there's a really powerful thing, like what you say out loud, what goes out of your mouth and back into your ears. For some reason, that feedback loop is very powerful in the brain. You know, it matters what you say out loud, you know? And so anyway, I'm sorry we're still recording. These poor people listening to this. I mean,
That is so good to hear.